SPEC webinar of this year. And I can see we have more than 100 participants arrived. I know there are still some colleagues arriving, but I think we can slowly start. As usual, I will give the floor to my colleague Isabel to start this session. Isa, please.
Good morning, good afternoon, good evening to everybody, depending on where you are connecting from. So it's my pleasure to welcome you to this new webinar on glossalan soil spectroscopy. So my name is Isabel Verbeek and I work at FAO's Global Soil Partnership. Our webinar today takes us to Aberdeen, where our renowned speaker will introduce us to the fundamental steps required for an accurate assessment of soil MIR spectra. So before starting, I would like to let you know that the session is organized in a webinar format in which participants cannot activate their audio and camera. You can see also that the session is web stream on YouTube, and it will also be available directly from the YouTube platform. We will share the link. So you are encouraged to post your question in the Q&A box, which will be moderated by some colleagues, and we will choose, we might choose also a few questions at the end to be answered live. All the rest will be answered via the Q&A. You can see also there is a chat box available that you can use for interacting between participants. So for any technical issues, you can write to me directly on the chat and I will be most happy to help. So before digging into soil spectroscopy, I will stop sharing the screen. Okay, so before digging into soil spectroscopy, with our speaker, I will provide a bit of background on the Global Soil Partnership and glossalan. So let me share my screen. Okay, sorry about that. Okay, so the Global Soil Partnership was established now exactly 10 years ago. We actually celebrate our birthday, our 10-year anniversary a few weeks ago. So it's a mechanism that was developed to have a single strong voice on soil issues and improve collaboration between all stakeholders. So it's a unique framework for exchange of experiences and discussion among many actors. So there are 7 regional soil partnerships, over 500 partner institutions worldwide, and a number of technical networks. And the glossalan, in which the spectroscopy initiative is included, is actually one of the technical network. So we have public and private donors also supporting GSP action on the ground. So we are supported by the ITPS, which is the technical intergovernmental technical panel on soils, composed of 27 soil experts, and we are also supported by the GSP Plenary Assembly, which is a decision-making body of the GSP. You can see here a number of areas of work, and my colleague Yi can put the link to the GSP where you can find further information. So glossalan, it was established in 2017 to build and strengthen the capacity of laboratories in soil analysis and respond to a need to harmonize soil analytical data. So in 2020, the glossalan initiative on soil spectroscopy was launched and it also together with the International Network on Fertilizer Analysis. And in the last 2 years, we've been consolidating this through the organization of capacity development and activities on soil spectroscopy. You can see here some screenshot of materials that have been developed, and also my colleague can certainly share the link. So here we are. This is the last session of this first term of webinar, and there will be more webinar coming up in September this year. So I will stop sharing my screen, and without further ado, I will now ask my colleague Yi to introduce our speaker, and he will be moderating this session. I thank you very much for your attention and wish you a very nice webinar.
Thank you very much, Isa. Welcome, colleagues, to join this session, the third session of the Growth on Spec webinar. And I have just shared the link of this, our first training material in the chat box, and it's free of the download. You are welcome to download this training material. And also, we are going to publish 5 series of the video courses, and we will let you know when it's online. Those 2 materials are complementary to each other. It will be a very good starting point to learn soil spectroscopy. So now I'm glad to introduce today's speaker, Dr. Jim Robertson, to talk about the interpretation of the soil spectra. Compared to previous sessions of the soil spectroscopy webinar, we are going a little bit deeper. Instead of talking about the estimation different soil properties, we are talking about the interpretation of soil spectra, which is rather important than just about estimation soil properties. And especially, it's very important, as a soil scientist, I think it's very important to understand what the soil spectral information give us, what soil spectra give us exactly the information, and instead of just focus on the estimation of soil properties. So Dr. Jim Robertson also has a very interesting experience. She grew up in Africa and back to Scotland and working in the James Hutton Institute as head of the IAS section over 15 years. So I think her experience and knowledge definitely deserve to share to the community for us to learn how to further develop soil spectroscopy in a different perspective. So without further ado, I would like to give the floor to Dr. Robertson. The floor is yours, please.
Good afternoon, everybody. I'll share my screen and that will be working. Can everybody see that now?
Yes.
Yes, perfect.
Okay, good afternoon, everybody. I'm really pleased to be here to come and share some information with you about how to interpret mid-infrared spectra of soil, which is something I've been working on, as you said, for some time. I work at the James Hutton Institute in Aberdeen, which is an institute which covers both environmental and agricultural research. So we do quite a range of different soil research, and hopefully you'll see some of the types of things we've been doing as we go along, and also get some information. So mid-infrared analysis of soil. What, as I say, some of you may have done this before, some of you may not have even heard of it, but definitely it's something which I think can be used very usefully to give us information about the soil, which we might not get in other ways. And as I say, the interpretation, not necessarily straightforward, but there's a lot of information that can be gained through that. And I'm hoping that through my presentation today, I'll be able to give you some insight as to how it can be used and how you go about interpreting it. Now, I'm not expecting that in an hour, everybody's going to be able to do interpretation of soil. It's very complex, but hopefully you'll get an insight and some pointers as to how to go along it. So what I've got here is an infrared spectrum that I've shown. I'll explain more about how we get it and what it means. But basically, we have a whole load of peaks. The question marks are telling us, are saying, yeah, what's it all about? How do we work out what this is telling us? So the outline, I've just outlined what I intend to cover this afternoon so you can get a rough idea. I'll start with an introduction to infrared spectroscopy in the mid-infrared region and the sort of spectra you get from soil samples. Now, for some of you, this may well be very familiar, but for other people, it might not have come across it before. Then I'll give some examples of how this interpretation of mid-infrared spectroscopy, that approach can be used in analysis of soil, and the applications, the things that we can apply it to, and places that we can get insight by doing this interpretation. Then it's more on a technical side, move on to how we approach the interpretation of the mid-infrared spectra of soil, things such as spectral quality, sampling methods, sample prep, and the procedure we go through for interpretation. And then I'll move on to have a look at some of the features of organic soils and some of the features of mineral soils, just so you can get an idea of the sorts of things we can pick up in these spectra. And then a short summary at the end of the different steps that you might want to go through when you're interpreting your mid-infrared spectra. So the infrared region is part of the electromagnetic spectrum. Sort of heat is what we're used to thinking of it as. And within that, you get the near, the mid, and the far infrared, and they're all in slightly different frequencies or wavelengths. So what we're talking about here is the mid-infrared, which if you do in wavelength is 2.5 to 25 micrometers. But we very often use, as spectroscopists, use a different scale. Because the numbers don't work very well in that region, we tend to use something called wave number, which is what we call a pseudo frequency. It's 1 over the wavelength. So it varies as frequency, but it's not the exact frequency. And the range for the mid-infrared of this is 4,000 to 400. Now, the interesting thing about infrared radiation and why we can use it for analysis is that the energy of infrared radiation, of that radiation, corresponds to vibrational energy levels within molecules. And what that means is that molecules will absorb that radiation depending on what is in them, what bonds there are. And because of that, that means that we get information as to what's in a sample from how it absorbs the infrared radiation. So just looking at some principles. Some of this, as I say, if you haven't a background in chemistry or in the physics of it, might not mean a lot, but it's just to give you some background. And as I say, it won't hinder, not understand, if you have are not familiar with this won't actually hinder you from using the technique, but just to give you some background. So basically, as I said, the molecules that are present in our sample will interact with it. It's the electric vector of the infrared radiation. It's electromagnetic radiation, but the electric vector interacts, and that results in absorption at different frequencies. Now, compounds have to have covalent bonds and exhibit a change in dipole moment during their chemical bond vibration to be IR active. Now, that's a statement which, if you haven't done chemistry, will not mean anything to you, but basically is just to say that not everything is infrared active, but the majority of things we look at are. So there's a certain sort of rules as to how things are absorbed. Group, for example, something like an OH bond from water or from a polysaccharide or something, each of them that will be vibrating, and different groups might have more than one frequency because there might be more than one vibration they're involved in. So within your spectrum, there could be a range of different chemical bond vibrations. For example, a bond might both bend and stretch at different frequencies. Sorry, go back one. So just to give you an example, a very simple example is bending and stretching for a water molecule. So here we have an oxygen with 2 hydrogens attached, and we can see that there's 3 different ways in which it can vibrate. It can do symmetric stretching, which is where both the OH bonds are stretching at the same time. It can do anti-symmetric stretching, where one bond is being compressed as the other one's being stretched. And it can also be bond bending. And the reason it might not seem that relevant, but what it's telling us is that even for simple molecules, you can get different vibrations, each of which will absorb at a different frequency. So we might see several bands from the same grouping within our spectrum. So having a quick look at the comparison between mid-infrared and near-infrared, I say many of you who've done soil spectroscopy already may be more familiar with the near-infrared, which is shown on the right-hand side. And we tend to display that in wavelengths with using nanometers. Now see here I've put 1100 to 2500. It can be regarded as being 780. Just the instrument we have only operates from 1100. So near infrared, as I say, we tend to do nanometers. The mid infrared, we have these wave numbers. The fundamental vibrations of bonds are the ones that absorb the IR light in the mid infrared region. And the spectrum that we get has a fingerprint, gives a fingerprint of all the absorptions which that molecule undergoes. And what we do is we get a very complete profile of inorganic and organic compounds. And for soil, this is really important that we can see inorganic species as well as organic. In the near infrared, it's combination bands and overtones of the mid-infrared fundamentals, and tends to be a little bit more difficult to interpret because they're not so well resolved and they're not so easy to attribute to fundamental vibrations. And so in terms of interpretation, it tends to be a bit overlooked. But there are advantages in terms of sampling methods, and also the fact that NIR has more energetic radiation, so it can penetrate deeper into sample. So these are the two types of spectroscopy that we commonly use for soil. Now, there's a whole range of different instruments that you can use for doing your analysis. And this just happens to be a picture of the setup we have in our own lab in Aberdeen. And it's a Bruker Vertex 70. So we need an infrared source, which is in here. Then we have to have a sampling compartment, somewhere to put your sample in for the radiation to go through, and then a detector, which is going to work out which parts or which frequencies have been absorbed. Now, in this particular case, and what we use quite commonly is something called a DATR sampling accessory, and I'll explain a little bit more shortly about what that is and how it works. Basically, it means diamond attenuated total reflectance, and it means that it's a method where you can just put you've got a small window that you can place your sample on. So as I say, it's a bit different from doing the diffuse reflectance, but it also, as I say, is something which we commonly use, and I'll explain how it differs from the reflectance. And in our setup, we also have a microscope, which means that we can do infrared microscopy on small portions of samples that are 100 microns square, down to that kind of thing. So the infrared spectrum, just going down to a basic thing, we can present it in two ways. We can present it as a plot of transmittance versus frequency. And at the top, if it's presented this way, at the top, straight line at 100% transmittance means that the radiation's going straight through. We're not getting any absorption. And the bands pointing down are at different frequencies. And so this is the bands that we will look at to work out what is in our sample. Alternatively, it can be plotted as absorption versus frequency. This time, the absorbance is going up in this direction, so the bands pointing up are the places that we identify the frequencies. So just to let you know, it can be presented in either way. I tend to work mostly in transmittance, though the absorbance, if you're doing, there's some work that you're doing, should probably best done in absorbance. So thinking about the mid-infrared spectra of soil samples, as I said, Fourier transform infrared. Now, the term Fourier transform relates to how the instrument works. So it was an FTIR spectrometer we use. As a spectroscopist, we commonly refer to it as FTIR spectroscopy because we assume it's being done in the mid-infrared region. Soil spectroscopy, because it was built up using the NIR more, tends to use the term MIR. So if I use them interchangeably, excuse me, but it does mean the same thing. So this is what's produced when the infrared radiation in the mid-infrared region is absorbed by a sample. And it gives the overall chemical profile of the soil. And this is an example here below of an organic soil with a small amount of minerals. And it's really important that the FTIR spectra can provide information on both the organic and mineral components of the soil, because that means that we get everything. We can look at the organic matter, and we can look at the the minerals that are present all at the same time. And we can see what the proportions are of organic matter to minerals, or different minerals to each other. And as I say, the absorption bands in the spectrum that we see, in this case, it's done as presented as absorption. The bands pointing up can be related to fundamental vibrations of functional groups. So, and a paper I refer to here, it's an article. It's not it's in a technical journal rather than an academic journal, but it gives you an overview of using mid-infrared and NIR for soil spectroscopy, if anyone's interested. So now thinking about the kind of applications we can use this for, why would we actually want to visualize the spectra? Why would we want to look at soils, and what could we see if we were using them? Well, in this particular example here, the spectra, which they're all displaced relative to each other just for the purposes of the display. But essentially, each of these spectra are a spectrum of a different horizon in a pit profile, going from the top soil right down to the lowest soil horizon. And this is an example from the National Soil Inventory of Scotland data set. It's a spatial data set which was resampled in 2007 to 2010 on a 20-kilometre grid across Scotland. So spatial data set. So this is an example of one of the soils. And what we can see here at the moment, it might, you might spot some differences, but you won't necessarily know what they are. But what it's actually telling us is that at the top layer, we still have got, we've got organic matter, and we can tell some of the functional groups that are present. We then have a bleached layer below it. Then we have some organic matter, which has been much more humified. And then even lower down, we have more organic matter, which has been washed through the profile. Then as we go down, we end up just with the minerals present. And as I say, at the moment, I haven't said anything about what all the bands are, but just to give you an idea that we can actually see this progression, we can see exactly what's happening or what's different about each of the horizons. Another example from a study did with a PhD student called Liz Young, and is published in Cathana, was looking at how some transects, as we move from a coast to inland on some of the Scottish islands, some of the Macar soils that we get there, looking at how they changed as we moved along the transect. And what we found was that in some places, there was a very big change from a soil which had a lot of carbonate in it near the coast to something which was purely silicate based as you got inland. On the other hand, we had other transects we looked at where there was very little change. The carbonate remained in a high proportion relative to the silicate. And what we were trying to do was associate these differences with the how likely they were to be wind eroded. So again, give us an insight into seeing how different the two soils were as you moved inland. Something a bit different and probably not kind of routine for people who are doing soil spectroscopy is using it for forensic purposes, can be used for evidence. An example here at the top on the left-hand side was a case where some treasure trove had been buried, and some treasure was found, and there was a dispute as to whether it was the original burial place or whether it had been reburied. And by comparing the soil, the top trace from the place where it was found to the traces of soil in the ridges of the artifacts, we could see that the two soils were very different, and we could establish that it was highly likely that the artifacts had originally been buried somewhere very different and then reburied. Similarly, we can also we have also used it to see whether we could link soil found on a suspect's footwear to soil at a crime scene. And soil evidence is not like DNA in that it's not as specific, but you can still get a lot of evidence because you can compare both the mineral parts and the organic matter parts and see whether you get a close match. In this particular occasion, we did actually get a close match, and as I say, it provided a strong suggestion that the suspects had indeed been at the crime scene. And there's a paper here again in a spectroscopy magazine, which also looks a bit at how to using soil spectroscopy for this type of thing. Another thing we can do is looking at peat condition. Peatlands can be eroded, they can be degraded, will change from top horizons to lower horizons. And by looking at each of the horizons, we can see any changes and we can relate this to peat condition. I have to say this particular peat didn't change hugely in condition, but that's also something which is of interest. Another way that we've used this type of interpretation is in characterizing soils under different long-term treatments. This was some work done as part of an AHDB, that's the Agricultural and Horticultural Development Board project on soil rotations that we did in this part along with colleagues from Rothamsted, and we used some soil data sets which have been under long-term treatments. And when I say long-term, they started in the 1800s, so like 150 years worth of changes. And we looked at variation in a couple of series of soils that had different additions, farmyard manure compared with NPK and MG addition, and an unfertilized control. And so we picked 8 time points over 150 years to look at how these samples varied. Now this is just preliminary results of one of the sorry, I hope everybody was able to hear there. I seem to have lost the connection. This is variation in plots between, we saw variations in the treatments between the different treatments at one point, and also when we go to a different, much later date from 1889 down to 2008, we can see quite clear differences between those. So the differences are subtle but evident, and we still have some work to do to unravel exactly what's going on. But this technique of interpreting the spectra has given us some information which we wouldn't otherwise have been able to have. So that's some examples of how you might use it or how we have used it, but how do we actually set about working out what it all means? How do we start to look at these spectra and work out what's happening? The first thing that we want to do when we're approaching infrared spectral interpretation is you want to start with good quality spectra. If you have poor quality spectra, you're going to make it very difficult for yourself. So ideally, you have a good signal to noise ratio, so not a lot of noise, and you also have no water vapor spikes or carbon dioxide interference. And your most intense band should be less than 2 in absorbance. That means that they shouldn't be bottoming out. They shouldn't be, they should still be all clearly resolved. And here we've got an example of a poor spectrum, which has got a lot of water vapor. And you can see it makes all the bands difficult to determine exactly which ones, to determine what is an actual band and what is coming from the interference. Now, there's different sampling methods that you can use for infrared spectra, particularly in the mid-infrared region. You can use FTIR spectra, or mid-infrared spectra, so probably should have said of soil, can be recorded using a range of different methods. You can use transmission, where you have to take your sample and form KBR discs or something to put directly in the beam. You can use diffuse reflectance, which many of you may be familiar with and is like what is often used in near infrared. And you can use the attenuated total reflectance that I referred to before. And the thing about both the diffuse and the ATR is that they can also both be recorded in the field. We can do that on using a portable instrument. So that's worth bearing in mind. However, the thing about the diffuse and the ATR spectra is that they look very different. If you look at the example here, the top one is a diffuse reflectance spectrum of a soil, and the bottom one is the ATR of the very same soil, and they look totally different. Now, the issue when it comes to diffuse is that if you use neat soil, effectively it's too strong, and what happens is all this bands down around 1,000 or sometimes near 1,400 if you have carbonates present can be inverted, and what you get is artifactual bands which become very difficult to interpret. It can still be used effectively for correlations, for developing calibrations, but they're not nearly so easy to look at. And if you actually do diffuse of organic soils, often what you get is one just broad lump with only a few little bits and pieces on it. You don't see all the individual bands. So it pays to be aware of this. If you did want to use diffuse and get spectra that look more like the ATR spectrum below, then you could dilute your soil with KBR or something like that, and then it will bring it down into it so that it's not too strong an absorber. And a really good paper for explaining all this is this paper in the Australian Journal of Soil Research from 1991. It's an excellent paper for describing what you see in, well, not so much ATR, but comparing transmission and different types of diffuse. And also, as I say, there's a paper that a proceedings paper from the Global Workshop on Proximal Soil Sensing in 2019, which I did along with Johanna Wetterlin, and it also has examples of this. So the ATR accessory that we use, this is what it looks like. There's a tiny window there. It's only about 1 millimeter or more, a couple of millimeters across, and where we put the sample, we have to apply pressure to have the sample in contact with the window. And basically the beam, it comes up, it is bent by a crystal. In this case, we use a KRS-5 crystal, which is a thallium bromoiodide crystal, and it penetrates the sample just a small amount before coming back to the detector. And so it works very, it's a nice and simple, straightforward way to do it. So there's advantages in using the ATR accessory. Sample can be placed without processing on the window, although to get good quality soil spectra, I'll describe how we usually do some processing of it. However, it's perfectly possible to put soil on directly. You just need to be aware that the spectra you see will differ quite a bit from the process spectra. It's non-destructive, so you can recover your sample after use. You only need a very small amount of sample to do it, approximately 1 milligram. And because it's got this diamond window, the DATR starts a diamond, we can do soils with hard particles and we don't need to worry about damage. And the IR beam only penetrates by a few microns, independent of sample thickness. So with no absorbance issues, we don't have to make any kind of allowances for that. And the main thing in terms of this is that the spectra are transmission-like and easy to interpret. Another thing to bear in mind is that the optics are all internal, so we've no issues with lighting conditions. And that's equally the case when we go into the field with a handheld. The other thing to consider, one of the other things to consider is your soil sample preparation protocol. It's important that the spectra you're looking at are representative and reproducible. And we determined a protocol for our highest quality spectra in the lab is that the sample should be dried and milled to less than 2 microns. Now that isn't always necessary, but in terms of when we were preparing the spectral databases, we wanted our best possible spectra, and this is how we achieved it. And so we developed this to get the optimal particle size while avoiding problems of contamination or degradation of samples. And the proceedings paper from 2013 that I mentioned there describes in detail what we did and how it worked. So as I say, essentially we use Macron milling with agate barrels, and then we air dry the sample and lightly grind it to get the exact conditions that we want. Now, I've just briefly put this up here, just some examples to show that what you do makes a difference to the spectra. The top example shows how the milling time changes what you see, because when you bring all the quartz particles down into the size range, the sort of few micron size range, they start being absorbed, and you see a much stronger spectrum from that. And so again, not expecting everybody to take in all these things, it's just to let you see that there can be things you need to take account of. And also we found some odd things happening sometimes when you use particular systems. You could get some degradation of the organic matter, and particularly when we use a tungsten carbide mill with a tungsten carbide ball. And so it's just really to highlight that you need to think and be careful about what your preparation methods are. So how do we actually go about it? We've got the spectrum. This is an ATR spectrum and it's in transmission. How do we go about it? Well, the first thing is just usually start at the left side, the high frequency end, and we move down, noting down the frequencies of the most intense absorption peaks. Now you'll find that if you're doing this in your software, there should be a cursor that you can put on to give exact frequency of each peak, or there might be a peak pick facility that will pick the peaks for you and give you the frequencies that you require. Then once you've done that, you want to think a little bit about your sample. For example, is it largely mineral or is it organic? And then with that, bearing that in mind, for example, if you have a soil which you know is only 1% organic matter, it's highly unlikely that the strong bands you see are going to come from an organic component. They're likely to be mineral in origin. So that's the kind of thing you want to think about. And then assign the most intense bands first using correlation tables or a reliable paper. And then sometimes, so you move through you always find, no matter what you're analysing, you always find at the top end, the high frequency end, you find the things like OH, NH, CH, And then further down, you get the double bonds. And then later down, even further, you get things like the SiO at even lower frequencies. So you work through that, seeing what you think you've got in it. And if you've got something you think you've got a carboxylate around about 1600, then there should also be a band about 1430. So have a look for some of these things just to see if you can find a second band which backs up what you think you've got. And also, for example, if you find a band you think is an amide 1 band, which is about 1650, there should be another amide 1550, and then see what other bands look like you think they should be. Assign other bands as needed. Then it's a good idea to write down the soil organic matter functional groups and or minerals you think exist in the sample. Now, you might not have been able to make up much of this organic matter, or you might pick up a few things, but you might pick up some minerals, or you might think that you've got a particular clay mineral present or whatever. Then at that point, it's quite good to get some help from spectral libraries or interpretation software. So, for example, if you think you might have kaolinite in it, then if you can find a reference spectra and compare that to your soil, you should see more than one band that's coming from that. So the software should not be used just to click a button and try and get a match, because that probably will give you wrong results. But it can be used to help back up what you're thinking you're seeing in your spectrum. Now, before I move on to looking at some of the spectral features that you get in the different types of soil, I just want to mention that although my talk today is about using it, the ATR spectra of the mid-infrared for interpretation, can also be used for correlations and to predict soil parameters in the same way that the diffuse or the NIR spectra can. And in fact, we can get some very good results, or we have achieved some quite good results, for example, for prediction of soil organic carbon. And there's a paper last year in Geoderma that my colleague Reza and I published, which gives the results for work that was done on the National Soils Inventory of Scotland dataset. So now on to looking at some different soils and what we might actually be seeing. We're starting off with spectral features of organic soils. So they're often referred to as peats, and they're accumulations of partly or completely decomposed plant residues, and it's generally often under anaerobic conditions because they can be underwater. Now, their spectra that we see will be related to that of the undecomposed vegetation, and so the peat that spectra will differ according to what the plant population is. But it will also differ from the vegetation depending on the extent of decomposition. So here I've given an example of two types of undecomposed vegetation. The first one is a sphagnum, and the second one is a heather root. So both can be found in your peat, and we see that they've got bands in many of the same places, but they do vary. So as I say, these will both have an input into the peat. Now, the major components of plant materials are cellulose and lignin. And key frequencies of these spectra can be identified in the spectra of vegetation and peat samples. For example, as I say, that you get a peak in the OH region at 3333 approximately, and you may often see that in peat spectra. That is indicating that you have got cellulose present. So key frequencies from this can be identified in the spectra of your vegetation and peat. And here below, we've shown a comparison of the root spectra that I had earlier and the lignocellulose and a material, and you can see that there is a lot of similarity in what's there. In addition to the cellulose, which is a polysaccharide, and the lignin, the organic soils, which are largely undecomposed, and often at the top of the peat, are likely to have other polysaccharides esters, protein, functional groups, all identifiable in the spectra. And generally, the CH stretching region of these soils shows no distinct peaks. This is the round 2920 to 2852. It's like a broad envelope, and that's typical of things which are derived from, of CH derived from polysaccharides. When the organic soils are more decomposed, which is often deeper in the peat, they're likely to have reduced polysaccharides. And if you look at the diagram below, the band at about 1023 is very strong in the top spectrum at the 10 to 20 centimetre depth. As you go to a lower, you go to 60 to 80 centimetres, you can see that it's no longer the strongest peak, it's a lot weaker. And that's evidence that the polysaccharides have been decomposed. Some ester may remain at the lower depths, but we normally find that we've moved from having ester present to carboxylic acid. So this band at 1730 has now become a band at 1705. And also in the CH stretching region, you'll see we've moved from having this sort of polysaccharide envelope to having some very sharp peaks which relate to CH2 bonds, so that's long carbon chains. So we can, all these differences tell us something about the changes in the peat condition as we go down the profile. But it's also possible that exposed peats will undergo changes similar to this. Now, most peats can be a lot of organic soils and entirely organic matter, but there's often a small amounts of mineral or mineral in different proportions. So frequently, even in almost pure peats, there can be traces of quartz and clay minerals kind of being blown in on the wind at some point. And why this is important is because there can be interference between the minerals present and the polysaccharides. For example, the SiO stretch is a very similar position to a CO stretch of the polysaccharide. So you just need to be aware that if there are minerals present, it will alter the spectrum that you see. So here's an example of a soil with, which is largely organic, but has some mineral present. And you see I can indicate all the different components that we can pick up there. We can pick up the small band at the top, indicates kaolinite. Then we can also see quartz bands arising from quartz. And the fact that there's quartz and organic matter means that this big peak just above 1,000 will be a combination of silicate and polysaccharide. And then if we look to more detail at what organic components we can identify, the sharp bands here, CH2 bands just below 3,000, indicate long chain or waxy components. The OH is coming from polysaccharide largely. And then we can see there's bands attributable to ester, carboxylate, protein, and lignin. So all these things we can unpick it all and work out exactly what we get. And every peat you look at will have a slightly different pattern. If you want some more information on this, the paper that we published, Arts et al. 2008 in Soil Bio and Biochemistry, is one which will give you a lot of relevant background. So we'll say, well, it might well be that many of you are working with agricultural soils or mineral soils and say, well, the peat and the organic soils are not really relevant. Well, they aren't, except that the bands that we see in the peat soils are also the same kind of bands which might be present in our soil organic matter. So much of what we did in interpreting the spectra of organic soils is also useful when it comes to assessing the nature of the soil organic matter in mineral soils. And in the top horizons, if we look at top soils, the soil organic matter often can still have functional groups which are identifiable. In lower horizons, sometimes you get humification, which can lead to a smoother profile in the spectrum with no distinct bands from the functional groups discernible. And some of these broad bands arise from carboxylates. So that is salts of carboxylic acids are often found in the lower, can be found in the lower horizons. And here I'll just give you a couple of examples of spectra of the humic acid that you can get in soil. This is a pure material that's been extracted from a mineral soil, and we've done the spectrum of. And that can also be found, it can be found in the acid form or in a carboxylate form. And this is, as I say, the sort of thing which can be present in your mineral soils. Or we can have the fulvic acids, the difference being that the fulvic acids are more soluble and plant available than humic acid. So just to give you an example that there are things that we can look at from the mineral soils where our interpretation from the organic soils would be useful. So now to look more specifically at spectral features of mineral soils and what we might see. The picture here is actually the mineral soils actually from just in front of my house on the farm, and that's a typical mineral soil from this part of Scotland, and it's got would be a few % of organic matter. As I say, mineral soils, so by definition, they have low soil organic matter content and are predominantly inorganic. Now, luckily for us, as I say, inorganic compounds do have an IR spectrum if they contain, as I mentioned before, covalent bonds or have water of hydration. All the majority of minerals in soils do have covalent bonds because they're SiO or CO from carbonate are all covalent bonds within those entities, and all of them absorb the radiation. And frequencies for IR spectrum of the minerals can be found in assignment tables. And a very useful book, which dates back to 1974, but is still used very widely worldwide, is by a predecessor of mine from my institute, Colin Farmer, who was the editor of the Infrared Spectra of Minerals, which a monograph which was published, as I say, back in 1974, and still, as I say, widely used if you can get hold of it. When we think about minerals and soils, usually we're dominated by silicates and sometimes also carbonates, but we do also get other soil types. So, for example, ones containing gypsum, which is calcium sulfate. And here I have an example of a gypsum soil, and it's compared compared to a sample of pure gypsum underneath. And if you can see the bands at 593 and 671, and then also 1683 and 1620, very sharp bands in the gypsum, which come through very strongly in the gypsum soil, which also has some carbonate and some silicate. But for some we published a paper of soil about plants growing on gypsum soils back in 2014 in PLOS ONE, and that's got some information about the types of interpreting spectra, both of the plants and of the mineral thing, which might be useful if you're interested in that. Another place where the infrared can be very useful in terms of mineral soils is discriminating between different carbonates or silicate minerals. So, for example, you can determine whether the carbonate that you have, if you've got calcium carbonate, you can determine whether it's calcite or aragonite, or whether it's a calcium magnesium carbonate, which is dolomite. Each of these have a difference. They have spectra which have some sharp bands at round about 870 and then lower down the 700s, and which are distinct and diagnostic for each of these things. So it is a very kind of ready way to determine between these. And we actually find that carbonates are picked up at very low levels in infrared spectra, so it's a very useful method for detecting and determining which type you've got. So here's just a standard sort of Scottish soil, mineral soil. We pick up kaolinite at the top end. Where the OH stretching is, you get the clay minerals because they in themselves have OH bands present, and they're what we call free OH, which means that they're distinct sharp little bands which can be very useful for determining what clay minerals you've got. Then we have a broad silicate stretch, which will be partly quartz, which these other two bands lower down are, and partly from the kaolinite. And we've just got a broad kind of hump that's coming from organic matter. So, but by looking at this spectrum, instantly we can see roughly how much organic matter there is, whether there's some but not a huge amount. And we can also determine that there is a kaolinite clay mineral present, whether it's dominated by the quartz. And so the proportion and nature of the clay mineral can be determined just by looking at the spectrum. And as clay minerals can be really key to soil properties, we'll have a quick look at them in a little bit more detail. So this is a spectrum of pure kaolinite, and interpretation of the IR spectrum with single mineral component in samples relatively straightforward if you've got a searchable mineral library. And as I said, the OH stretching part which is up above about 3600 is the key part for identifying that we've got this there. And each of these bands are OH. Further down we get the bending and we get the SiO stretching. And if we look in detail at the OH stretching region, you can see we've got quite a distinctive pattern. And that, as I say, tells us not just that it's kaolinite, but something about the type of kaolinite that we've got. Because if you are interested in determining exactly the nature of these minerals, you can decide what you can look at them, and there's differences between well-crystallized kaolinite, poorly crystallized kaolinite, and also dicite, which is formed slightly differently by packing in a different way. So it's a very sensitive method for looking for clay minerals. And here's some examples of some different types of clay minerals. The kaolinite that we've already looked at, gibbsite, which is an aluminium hydroxide, and then montmorillonite, which is a swelling clay. And as I say, we actually run a course at the Institute. We haven't done over COVID, but we'll hopefully get back to doing it, where we do a course where we look at analysing clay mineralogy through infrared, XRD, and SEM-EDS. And as I say, there's a paper we published on, it's actually on the looking at halloysites, which will give you an idea of how the infrared can be used to do this. And this is just showing the differences between the spectra. So just coming down to the summary of the factors to consider when you're looking at, when we're trying to interpret spectra. First thing is try to avoid interferences by moisture and CO2, because that will make it very difficult for you. Be aware that although you can interpret spectra of soils of a range of different conditions, that how you prepare it will change a bit what you see, and you need to ensure that you're doing something the same each time so that what you've got is representative and reproducible. And be aware that different sampling methods will cause large differences in the appearance of spectra, and you need to take this into account when interpreting them. Again, as I said, good quality data will make things a lot easier for you. So as well as the no water vapor or carbon dioxide, try and get a good signal to noise ratio so that you don't have a lot of noise. And also you don't want the absorbance to be overly strong so that the bands are not, the individual bands are not discernible. Take a look at the spectrum starting from the high end of the high frequency end, usually presented on the left, working down to the right, and note the frequency of the intense absorption peaks. Make sure you think about your sample and what you know about it, and so that what you're going to assign is going to make sense. For example, as I say, that you're not assigning in a very mineral soil a large number of bands to organic matter. If possible, look for secondary bands for functional groups, just to be, you know, if you think you've got something, like you think you've got kaolinite, you might look for the bands at the top, the small band at the top, but also look to check that you do have a silicate perhaps which agrees with it. Assign other bands as needed, and write down, as I say, good to note down what you think you're seeing and which minerals you think you've got, so you can then compare to reference spectra and see whether it actually makes sense. But also be aware, it's a very, very complex mixtures, everything's overlapping, and it's not something which will be, it's something which will be very, you know, take a while to get used to. But the main bands can be picked out quite readily. And finally, I'd just like to make some acknowledgements to all my colleagues who've helped me in this work, particularly in the infrared section at the Institute, where I have Angela Main, Reza Hagi and Tony Fraser, and a former colleague, Estefania Perez Fernandez, who did a lot of work for us. And also thanks to the many other colleagues whose research are mentioned in this from the James Hutton Institute. And I must thank both RESAS, which is the environmental wing of the Scottish Government, who provide a lot of funding, and also the AHDB Potato Board for funding for the research. So thank you for your attention.
Thank you very much, Dr. Robinson, for such a comprehensive webinar. I think it's a very valuable experience and knowledge you shared with colleagues in the community. And we saw a few interesting questions, and we decided to bring into the discussion after your presentation. And I think you also can see these questions from your screen, QA box. If you click QA box, and you can take a look, and I will read it out, because some colleagues will watch the video recording and they won't be able to read the questions. So I will just read it out. The first question is, if the molecular bonds that vibrated can be causing a spectral peak can be found in more than one functional group, which is often the case. What is the good approach, workflow, to finding the specific functional group in your soil sample? I think this is a question. Can write a book, we were thinking, so if you can just briefly explain a little bit.
It is difficult when you have well, there's two things. So if you're talking about, you can have, like, for example, the same bond, a CO bond can be from different functional groups. Yeah, I think we're talking about, but usually when they're part of different functional groups, they tend to have slightly different frequencies. So for example, if you are looking for an ester and an acid, there is a slight overlap in the frequency you would find it, but usually above about 1720, you would have an ester. Lower than that would be an acid. And generally, these, you have to look at the correlation tables. The correlation tables will give you an idea, because, for example, if you then move to something which was an aromatic acid, it might be lower still. So I think you identify the peak frequencies if you've got a specific frequency, and then you know that region maybe is the C double bond O region, which is around about above 1700. You then need to look at the correlation tables, or, as I say, a reliable paper which describes the range. Now, sometimes ranges overlap. It becomes more difficult to determine exactly what it is, but generally that's the way to do it, is to write down the exact frequencies, look at the ranges, and then see how it matches up.
Thank you. The second question I saw is about this colleague said he or she is trying to look for some organic functional group in her low carbon, less than 3% in mineral soil. Which spectral type is better, FTIR or ATR?
The diffuse, the thing about if you do diffuse reflectance spectra of a neat soil, we get the problems where essentially it's too strong, it's too strongly absorbing, and that's why we get the why we have some of the inversions and the artifacts. But what it does do is enhance some of the smaller bands. So possibly for the diffuse, as long as it's not too noisy, then you might actually see if it's a low organic matter soil, you might actually see it better in the diffuse. The alternative to that is trying to extract the soil organic matter, which has got issues in it on its own. But yeah, I suspect that for at 3% or so, you probably will see it in the ATR. I suspect that in the diffuse it will be that little bit stronger. It might be easier to look at the organic portion in that way.
Thank you. There is a question, I think, is regarding grounding soil samples. What can you say about soil sample ground to about 100 to 125 microns? Do they yield good or bad quality spectra?
I think that if it was ground to that level, you would still get quite good quality spectra. But what you won't necessarily it won't necessarily be exactly the same as if you can take it right down to the few microns. You'll know if it's more if you've got, when you grind it down to that, if you've got some small, you get some slightly larger particles, then you might end up with noisy spectra. So really, you can record the spectra and see what it looks like. Sometimes quite often we just do ball milling. If it's too noisy, then we'll mill it a little bit more and bring it down a bit further. I won't, if it's ground, if it's reasonably finely ground, which that is, you should still get quite good quality spectra. But as I say, it's a case of looking at it and seeing how noisy it is.
Okay, thank you. To complement your answer is just to let colleagues know that we are actually also planning for the coming webinar the next semester. I think one webinar topic already confirmed from one researcher from the United States that he will specifically talking about how the grounding affected the prediction results. So it's I think it's around September we will have this webinar. Another question I saw, another thing is I forgot to introduce. We have another colleague, the Reza Hashi, in our panelist, Dr. Hashi, and he is trying to help answer the questions also. And he chose to answer this question live. I don't know if he would like to answer or he would like Dr. Robson answer. Is it possible to measure MIR spectra in field by sunlight source? I think because of atmosphere distribution, this kind of spectroscopy just could be used in dark box or controlled condition.
I don't quite follow what I presume doing emission spectroscopy, which is a completely different thing, where usually if you take the spectra from the ground, you have to take out the heat element. Emission spectroscopy is a different thing from what we're speaking about, and it's not something that I've done. I think it is possible to get something out of it, but it's not a method that I'm familiar with.
Yeah, I have some similar feeling when I saw this question, because if you want to get a sunlight source, it's not normally talking about the remote sensing platform, the passive, but what we're talking about, the MIR spectra, that is something, the energy generated by the electricity. So it's a different definition, I think. Another question. I think I saw one question from the chat. Actually, it's thank you so much, Dr. Robinson, for nice presentation. I would like to know if there is a way to standardize the interpretation of spectra, since the different drift used to sample will result in different spectra.
The fundamental bands, the bands that are absorbing, are at a given frequency. That's regardless of what you're doing. That it's not the interpretation that changes. What happens with the diffuse is that you have by some of the bands being inverted, the points where they invert can lead to look like bands, and also the bands look as if they're pointing in opposite directions. So that means that what you're seeing is not actually band at the frequencies which correspond to the fundamentals. That's where the issue comes in. However, if you want to do diffuse so that you can see the bands at exact frequencies that relate to the vibrations and the different frequencies for different functional groups, what you have to do is to dilute your sample with mixing the soil with KBR or something else which is not infrared active, and therefore you will get a spectrum where you can still see it. So you can look at the band. What you have to be aware is that, for example, in the diffuse, the bands at the top, the CH and the OH from the clay minerals, will still be as they were. You will also see additional bands which are things like the carbonates will have overtones which will come in. So it's the interpretation doesn't change. It's just what you're actually seeing, that you're not actually seeing the bands, you're not seeing the fundamental bands. As I say, that paper that I mentioned, that paper from 1991, the Australian one, is excellent for explaining exactly. I mean, it's the one I think everybody should look at if they want to have an understanding of this, because it really is a good explanation of the differences that you see.
Yeah, thank you. I think I saw one last question is generally is asking how comparable is a mobile MIR analyzer for field analysis and a top bench analyzer for predicting the soil property. So basically is to see the field measurement and the level measurement.
Yeah. The actual instruments are the field. We've got two. We've got what was called an Exoscan, is now, it was an Agilent, became an Agilent 4100, and we have an Agilent 4300 as well as our benchtop ones. The quality of the spectra from them is just as good. The instruments are just as good. What the difference is when you go out into the field is that the soil you're analysing is wet. Well, not in Australia so much, but certainly in Scotland, it tends to be wet. It's got particle sizes. It's inhomogeneous, and the particle size is not ideal. So what you see is related more to the difference in the field condition. However, what you actually see is you generally see greater proportion of clay minerals and organic matter, because a lot of the minerals, the actual minerals, are too big to absorb. The surface is too big. They reflect the radiation rather than absorbing it. So you see something different, but it can also be useful. The biggest issue is around water, because obviously you can get a really wet soil, then you'll just see the water. So the comparison to the answer is that the instruments will produce exactly, as long as you've got a good quality instrument, will produce the same as the benchtop, if the handheld as the benchtop, if you're analysing the same type of sample. The difference comes from the fact that you're analysing soil with a different which is in a different condition. And the predictions, obviously, so the predictions of we're working on it at the moment, shall we say, the predictions from that.
Yeah, we still have some work to do in terms of the prediction before we really bring to the service. And actually, there is a question talking about the service, and this question is coming from YouTube live stream, because now we are doing this webinar from a Zoom platform. In the same time, we're also doing a live stream from a YouTube channel. So some colleagues, they had a problem, connection problem, couldn't join this Zoom session, but they are watching in the YouTube channel. They also asked the question. There is a colleague, her name is Melissa Lees. She's asking, what is the cost per soil sample using MIR equipment? Is there a laboratory that offers this service? But I think, if it's only for the MIR scanning, I have to say this is free. We don't cost anything, just you buy the instrument. But I guess there is some misunderstanding. Melissa Lees is probably, she misunderstood the instrument, the scan soil will simultaneously give the results of the soil property. But Jim, if you would like to say a few words regarding this question, also if you know if there is any laboratory offers this service.
I'm not. I think well, there are various places that do commercial mid-infrared spectra, but I'm not. But yeah, as I say, it's not something that I'm particularly familiar with, I'm afraid. I'm not sure which laboratories offer that.
For estimation soil property surveys, yes, I think in my memory there are a couple of laboratories that offer kind of a service like that. But I have to say, before we really bring this service to the market, we still have some work to do, especially in terms of the large scale. And current, yeah.
But I suppose in terms of getting, people, well, part of the thing with GLOSALAN is trying to get to make it available to people by, if they supply samples, that they can have the spectra recorded. So yeah, I'm not quite sure whether that's relevant or not.
Yeah, another thing I want to add is that GLOSALAN, we are currently working with partners to bring a free charge of the estimation platform for soil organic carbon online. So basically, everyone from the world, if you have a spectra, you can upload your spectra and get the prediction for free. So another question is a little bit interesting also. Are there any database that can be used for cross-checking peaks of different soil components?
There are various spectral libraries, but generally of minerals, which can be used. I can't think off the top of my head which one, because we've developed our own libraries. So so don't tend to use them so much. But there's also there's quite a lot of good books that has for example, will have the books that I mentioned, Colin Farmer. There's some other books that we also use which have in them have lists of what the frequencies are for particular components, particular clay minerals or whatever. But there are a range of things out there. The thing you have to be careful with though is if you get a spectrum of a mineral, probably check it from more than one place, or check that the purity has been done by XRD or something else as well, because there can be issues, and we've come across that before, where something which you get told is a spectrum of one thing is not that, or is impure and has got more than one thing. But yeah, there are a range of databases out there that offer spectra, mineral spectra that you can look at.
Yeah, thank you. I think today's webinar, we have almost 1.5 hours. And I believe we have shared quite a lot of information, and also we have some quite interesting discussion. I saw one question: what is the cost per soil sample using MIR equipment? It's the same question we discussed before. Yeah. So in general, that is the reason we want to apply the spectroscopy for soil analysis, because it's cost and time effective. Any deep learning machine model that have been used for prediction soil property, or comparison between different machine. This is regarding algorithm and a different modeling. Different modeling approach. I would refer our previous webinars. We have different webinars also talking about the different algorithm, and you are welcome to join our Facebook group. We also regularly share some nice paper publications and group. So please feel free to get information from it.
But we have, I think Reza's typing an answer to that, because the paper that we published in Geoderma last year was a comparison of different methods. So Reza was using the SVM and CNN 1 and 2 as long as comparison to partially squares, but that was for our ATR spectra. That was for our NIR spectra and our ATR spectra. So as I say, Reza, I think he's typing an answer to that, because that's his area. My area of expertise is more in the soil and the interpretation, and his expertise is in the modelling.
I'm just wondering, Reza, if you want to speak a few words instead of typing. Reza.
Yes, can you hear me?
Yes, we can hear you.
Yeah, just as Jim said, there's a paper that I can share with you, and that we, as Jim said, we compared 4 different methods. So, namely, partial least square, support vector machine, QBIST, and convolutional neural network, but using ATR in the MIR and NIR region. So not diffuse reflectance. So, but yeah, I will send the link to the paper.
Reza, and later on also, if you use Facebook, so you are welcome to join our Facebook group. And some of your new publications, also feel free to share your publications in that Facebook group. So yeah, all these knowledges will be able to deliver to the community. Yeah, I think Dr. Robinson, you also have been non-stop talking for 1.5 hours. I think it can be a little bit
And I practiced it this morning, and I realized by the end of it, I give myself a sore throat, but yeah.
Yeah, thank you very much for such a nice webinar, and it provides a lot of information, and I can see we have quite a lot of participants join the live session and also watching the YouTube live stream. And this web recording will be also uploaded to our website, and also the presentation, the PPT will also be uploaded to our website. So colleagues also will be able to watch the recording and download the presentation for your further study. And in the meantime, if you would like to get in touch with Dr. Robinson, and Glosonsberg will be happy to facilitate, because just now I saw one message from the chat, because the chat message is going very fast. It's difficult to follow, and they were wondering if it's possible to have, I think it's something talking about to have visiting research or something to in your institute, something like that. But please write a message or email to me, and I will be happy to make contact between you and Dr. Robinson. So thanks again for your contribution, and also thanks to the Dr. Reza Khash for your help and support. Thank you very much.
Thank you.
Thank you very much.